this lecture, we'll be starting with a new section of the subject operating system, and this section is called memory management. So under this memory management, we will be discussing two chapters. One is called the main memory and the other one is called virtual memory. So we'll be starting off with the first chapter, which is main memory, which falls under memory management, and we will see what do we mean by memory management and how does this chapter main memory play a role in memory management. Alright, so let's get started with this new section. So as we know, the main purpose of a computer system is to execute programs. So we know this very well, that the main purpose of our computer system is to execute programs. We have programs, we want to execute those programs, and we want to get results from those programs. Now, during execution, these programs, together with the data they access, must be in main memory, at least partially. Now, what do we mean by this? So, when we are executing programs in our computer, these programs that we are executing, along with the data that the program is going to access, must be present in the main memory. So, if not fully, at least partially, these data as well as the program must be present in the main memory. So when we say main memory, what do we mean? So main memory is our RAM, which is a random access memory. So when we have started operating system itself, we have discussed about main memory and secondary memory. So main memory is our RAM, which is volatile in nature. So whatever is stored in the RAM stays in the RAM only as long as the power supply is on. So when the power supply is switched off, whatever is there in the RAM is erased. So all our program and data that we have in our computer is by default stored in the secondary memory, which is like our hard disk or our solid state drives. And then when we want to execute a program, that program will be loaded into the main memory, which is the RAM. So this is what we need to keep in mind. So when a program is being loaded or executed, at least a part of that program and the data that it accesses must be present in the main memory. So now we can understand what is the importance of main memory in our computer system. So coming to main memory, let us discuss further what is this main memory and what are its uses. So when we studied about CPU scheduling, we showed how the CPU can be shared by a set of processes. So we have been studying about CPU scheduling, and we saw how the scheduling algorithms were there, and using those scheduling algorithms, how we are able to share the CPU between processes for an efficient usage of our CPU. Now, as a result of this CPU scheduling, what did we get? We saw that CPU utilization as well as the speed of the computer's response to its user could be improved. So this was the main reason why we were using CPU scheduling, to improve the CPU utilization as well as to improve the speed of the computer's response to its users. Now, to realize this increase in performance, however, we must keep several processes in memory. That is, we must share memory. So in order to achieve this or to realize this, we need to keep several processes in memory. That means we have to share our memory. So memory sharing is an important thing that we need to have in order to achieve CPU scheduling. So remember that the main memory is going to be shared between different processes. Alright, now let us try to understand what is this main memory and how is it different from the secondary memory, and how does main memory affect the speed as well as the performance of our computer system. So for that, let me take a small example here from our day-to-day life. So let us say that you have a bookshelf here. So what do we do with a bookshelf? A bookshelf is used for storing books. So think of the bookshelf as a secondary memory, and think of the books as our data or the programs that we want to execute. So when we are not using these books, we just store them in the bookshelf. It is a place for storing the books. Now, when you want to read a book or when you want to write into a book, what do? You take out the book from the bookshelf and you place it on a table. So think of this table as the main memory. So the table is something that we are going to use when we are going to read a book or when we are going to write into a book. So think that the RAM or the main memory is this table. The data is stored in the secondary memory when we are not using it, and when we want to use the program or the data, we take the data or the program from the secondary memory and it is loaded into the main memory. Alright, now let's say that your table is not very big. You are having a small table. If you are having a small table, what is the disadvantage? Let's say that you want to study from multiple books. So you need to take all those books, you need to keep those books on the table, and you are going to refer different things from the books, and you're going to study, you're going to write and do many things. But if your table is small, then you are not going to be able to keep many books on that table. And hence, you are going to be slow in studying or be slow in getting your task done. So in the same way, even if we have a big secondary memory, but if the main memory is small, then we are not going to be able to load many programs into this main memory, and hence it is going to slow down the performance of our system. Okay, so for example, in secondary memory, let's say that you have a program, let's say Microsoft Word. So we have Microsoft Word stored in the secondary memory, and it is just sitting there. Now when you want to make use of it, that means when you want to open Microsoft Word and when you want to type a document or view a document, what do? You will open it, and when you open it, what happens? That Microsoft Word will be loaded into the main memory. And it is from the main memory that you are going to access and execute that program and make use of the program. So I hope with this demonstration you understood what is the difference between secondary memory and main memory, and what is the importance of main memory, and how the size of the main memory plays an important role in the performance of our system. So keep this demonstration in mind when we are discussing about main memory, because it will be easy for you to understand. Okay, so coming to the topics to be discussed in this section or in this chapter, we are going to discuss about the various ways to manage memory. So we need to manage our memory, as we said, because we are going to share our memory between different processes or programs. So we need to study about the ways to manage memory. So this is a very important topic in operating system of how to manage memory. So we'll be discussing this, and we are going to discuss about various memory management algorithms. So under this we will be having primitive or bare machine approach, and we will be having paging strategies as well as segmentation strategies. So these are the topics or the main things that we are going to discuss about in this chapter of main memory, which falls under the bigger subtopic of memory management. So this was just an introduction to the section of memory management, and to give you a brief idea or introduction to main memory. So you may already know what is main memory. So let's get started and be introduced and get familiar with main memory, and we will be diving into the deeper topics of main memory as we go further in this chapter. So I hope this introduction was clear to you. Thank you for watching, and see you in the next one. Previous lecture we had an introduction to memory management, and we also had an introduction to main memory. So here, as we continue studying about main memory, here we will be discussing about the basic hardware structure in this lecture. Alright, so let's see what is the basic hardware structure and what we can learn from this. So as we talk about memory, memory consists of a large array of words or bytes, each with its own addresses. So think of memory as a large array of words or bytes, which is the data that is stored in memory, and each of them will have their own addresses. So memory, you can think of it as a block which will consist of large array of words or bytes. And how do we access this memory? We need to have some way to access this memory, and the way to access this memory location is by using their addresses. So this is a very important thing that you need to keep in mind, that all the memory location will have a specific address that is designated to it. Alright, and then the CPU fetches instruction from memory according to the value of the program counter. So we know that in our memory we are having the data stored, we are having the programs that are stored. Now when the CPU wants to make use of some data or program that is present in the memory, what it will do, the program counter will tell the CPU where is that memory location, or from where it is supposed to fetch that data. So the CPU will fetch that data or instruction from the memory according to the value of the program counter. And then these instructions may cause additional loading from and storing to specific memory addresses. So this is just a basic of how the hardware structure of memories work. So the main thing to keep in mind here is the memory addresses. Now let's see how a typical instruction execution cycle works. A typical instruction execution cycle first fetches an instruction from memory. So this is what I already explained. It is going to fetch the instruction from the memory, and the instruction is then decoded and may cause operands to be fetched from memory. After the instruction has been executed on the operands, the results may be stored back in memory. Alright, so let's take an example of a simple operation here. Let's say that we want to add two numbers, 2 plus 3. Now 2 and 3 are the operands. Now we know that these operands has to be stored somewhere in memory. So imagine that 2 is stored in one memory location and 3 is stored in another memory location. So if we want to add this, what will happen? We first have to fetch this 2 and 3 from their respective memory location. So we need to find the addresses of these memory locations of 2 and 3, and then they will be fetched. Now after they are fetched, it says here the instruction is decoded. This is because data is stored in memory location in different formats, and for the CPU to understand and execute them, they may have to be decoded. So that will be done, and after that is done, what will happen? The instruction will be executed. That is, the addition will be done, which is based on our example. So 2 plus 3 will be added, and what is the result? The result is 5. So after the instruction is executed, the result may be stored back to memory. So we need to store the result also to some memory location. So the addition or the sum of 2 plus 3, which is 5, that result will be stored back to some memory location again. So this is how a typical instruction execution cycle works. Alright, now moving on to the basic hardware structure, the CPU can directly access only two of these memories. What are they? First one is the registers built into the processor, and then the main memory. So the CPU, which is the central processing unit of our computer, it can access directly only these two things, which is the registers and the main memory. So what are the other things that we have apart from registers and main memory? We have many things under the secondary memory, like our disk drives, which may be your hard disk or your solid state drives, and we can have the external storage devices. All this comes under secondary memory, but the CPU can directly access only the main memory and the registers which are built directly into the processor. Now there are machine instructions that take memory addresses as arguments, but none that take disk addresses. So the machine instructions which are used for executing operations, they will take memory addresses as arguments. So when we say memory addresses, remember that it refers to the address of the data that is present in the main memory or the registers, and it will never take disk addresses as arguments, because as I said, disk addresses. So what do we mean by disk? Whenever I say disk, please keep in mind that we are talking about the secondary memory. So it is not going to take arguments as the disk addresses, but only the memory addresses. Why? Because CPU can directly access only registers and main memory. So any instruction in execution and any data being used by the instruction must be in one of these direct access storage devices. So as I have already explained even in the previous lecture, whenever we want to execute something, that program or that data that it is going to use must be present in one of these direct access storage devices, which is either the registers or the main memory. Only then the CPU will be able to access it and execute it. So if the data are not in memory, they must be moved there before the CPU can operate on them. Okay, so if the data or the program are not present in any of these two, then it must be first moved here from wherever it is present, and only then the CPU can access it and operate on them. Okay, now the next topic that we are going to discuss is the CPU cycle time for accessing memories. So we talked about registers and main memory. These are the two devices which the CPU can directly access. Now let us see what is the time that the CPU takes for accessing these two devices. So first of all, registers. Registers are accessible within one cycle of the CPU clock. Most CPUs can decode instructions and perform simple operations on register contents at the rate of one or more operations per clock tick. So in case of registers, CPU can access the data present in the register within one cycle of the CPU clock. So we see that this is a very fast accessing speed that we have. And why is this? Because the registers are directly built into the processor. So it is very easy for the CPU to access what is present in the register. It takes only one cycle of the CPU clock for accessing these registers. So we see that this is very fast. Now let's see what about the next one, which is the main memory. So for main memory, the access may take many cycles of the CPU clock to complete. In this case, the processor normally needs to store, since it does not have the data required to complete the instruction that it is executing. So in case of main memory, unlike registers, the CPU may take many cycles to complete. That means for accessing the main memory, the CPU can take more time because there will be many cycles involved in order to access this main memory. Because main memory is something different. It is not directly built into the processor. So in this case, the processor normally need to store. Now why do we say that the processor normally need to store? That is because, let's say that we are executing a program, and then there is a part of the program that is present in the main memory, and the CPU is accessing that. So it takes many cycles for the CPU to access that, and then it gets hold of that data. Now let's say that another part of the program which was not present in main memory is now loaded to main memory because now that is required. Now what happens? The CPU again have to go and access that. So in the first case, the CPU did not have the complete data that it needed for completing the execution. So it again goes to the main memory and tries to get that second part of data of that same program. So the CPU have to wait till it gets the complete information that is required for completing its execution. So in this case, the processor will need to store, or it will have to wait until and unless it gets the complete instruction for its execution. Now this situation is intolerable because of the frequency of memory accesses. So what is the solution for this? The remedy for this is we can add a fast memory between the CPU and the main memory. A memory buffer used to accommodate a speed differential called a cache. So this is a remedy that we have for this problem. So we have something called a cache memory, which is something that is present between the CPU and the main memory. So this cache is a very fast kind of memory, and then the things that we need will be stored in the cache memory so that the CPU can easily access and make use of the things that are present in the cache. So if a program is executing, if the part of it that is required is present in the cache memory, then what will happen? The CPU can easily access this, and it can avoid the numerous memory accesses. That means it does not have to go and directly access the main memory too many times, which will lead to slowing down of the entire execution. So if the instructions and the data is present in the cache, which is a fast memory, keep in mind, then it will speed up the execution process. So cache also is a type of temporary memory, but it is a very fast memory, and remember that it is like a buffer which is present between the CPU and the main memory, which will help in speeding up the execution. Alright, so that is about the CPU cycle time for accessing different type of memories, which we discussed here, registers and main memory, and then we saw the problem and the solution using the cache. Now we will come to the next topic, which is protection of the OS from unauthorized access. So the first problem that we saw was the time taken by CPU for accessing main memory, and we saw the remedy for this by using a cache. And now there is another problem, which is protection of the OS from unauthorized access. So we know that operating system and its data is very sensitive, and we should not allow the users to modify what is written in the operating system. Because if the users go and accidentally or deliberately modifies what is written in the operating system, it could crash the operating system or it could crash the system. So we need to protect the OS from unauthorized access. Now, how can we do this? So as I said, the operating system has to be protected from access by user processes. In addition, user processes must be protected from one another. This protection must be provided by the hardware. So as I said, operating system must be protected from access by user processes, and also we must protect user processes from accessing one another, because there will be one user process that is trying to do something and another user process should not come and interfere or modify that user process. So user processes also must be protected from each other, and this protection of the OS from unauthorized access as well as protection of user processes from one another must be provided by the hardware. So that is why we are discussing about the basic hardware here. Okay, now the question is, how can this be done? How can we accomplish this kind of protection? So in order to do this, we should ensure that each process has a separate memory space. And to do this, we need the ability to determine the range of legal addresses that the process may access, and to ensure that the process can access only these legal addresses. So in order to achieve this protection, we need to ensure that every process has a separate memory space. Now, what do we mean by memory space? So by memory space, we mean that a particular process should be able to operate or make changes only in that particular defined memory space. So we'll be defining memory spaces for each processes, and we will say that a particular process can only operate within that memory space that is defined. So here, as it says, we have to determine the range of legal addresses that the process may access, and we should ensure that the process can access only that legal addresses. So for example, if there is a process P1, we will say that process P1 should be able to access only the memory location from, let's say, 10 to 50. So only between 10 and 50, whatever addresses are there, only that will be accessible by process P1. So memory address 10 to 50 is a legal address space for process P1, and it should be able to access only that. But how can we do this? How can we implement this? For this, we use two registers called base and limit. So using these two registers, base and limit, we are going to practically implement this solution that we have just suggested. Alright, so let's see what is this base and limit and how can it be used for ensuring that a process will only access whatever is present within its legal memory space. So talking about base and limit, a base and a limit register define a logical address space. Now what do we mean here? The base register holds the smallest legal physical memory address, and the limit register specifies the size of the range. So think of this as our memory space that we have. So from 0 up to 1024000. So this is the memory space that we have. And on top of it, we have the operating system. The operating system is residing in the memory space between 0 and 256000. Alright? And then here we have different processes. For example, for this process, it can operate between 256000 to 300040. So this is the memory space of this process. And for this process, it is from 300040 to 420940, and so on. It is defined for each of these processes. So what is the use of this base and limit? So the base register, it holds the smallest legal physical memory address. So for example, we are talking about this process here, which I am pointing at. So for this process, the base is 300040. So the base is a register that is going to hold the smallest legal physical memory address. That means this process can start accessing from this particular memory address. So the smallest or the minimum memory address from which its legal address space starts. So that is what is stored in the base register. And then what is this limit? The limit register specifies the size of the range. So the size of the range. So what do we mean here? So here it says the limit is 120900. So that means starting from the base address, if we add this limit, then what is the memory location that we get? That is 420940. If you add these two numbers, you will be getting this number here. So that means from the base, if you add the limit, you will get the last memory location that this particular process can access. So that is what we mean by the base and the limit. So here, if the base register holds 300040 and the limit register is 120900, then the program can legally access all addresses from 300040 through 420940 inclusive. So that is what I just explained. So the base is the smallest legal address from which the legal address space starts for the process, and then limit specifies how many addresses starting from here it can access. So if we add these two, we'll get the last memory address that this process can legally address. So this is how, using base and limit, we are able to specify the legal address spaces of the particular processes. So a particular process will be able to access and operate only within its legal address space. So if this particular process tries to access memory location 0, it will not be able to access. Why? Because the legal address space for this process is only from this address up to this address. It will not be able to access any other address spaces. So the operating system is present here, it will not be able to access this directly because this is another memory space and it is not within the legal limit of this process. And also you see these are other user processes. For example, if this process tries to access or modify something for this user process or this, it will not be able to do it because, as we just said, the legal address space for this process is only from this address till this address. So here is a flowchart that describes how it works. So here, for example, there is an address that a particular process is trying to access. Now what will happen? So it will first check if this address is greater than or equal to the base address. Now we know that a process is able to access only that address space that starts from the base and goes up to base plus limit. So here, if it is greater than or equal to base, it will be able to access. We say yes. And in case if it is not greater than or equal to the base, that means if it is less than the base, what does it mean? It means that it is not within that legal address space of that process. So if it is no, we are not going to allow it to access that. So it goes to a trapped operating system monitor and it will throw an addressing error. Now let's say that the address that the process is trying to access is actually greater than or equal to the base. So it comes to the next flow here and it checks if this address is less than or equal to the base plus limit, because base address plus the limit is going to give us the last memory location that the process is allowed to legally access. So if the address is less than or equal to base plus limit, then yes, we can allow it to access the memory. If it is not, then it is not allowed and it throws the same error. So this is how the checking is done to see if we should allow a particular process to access the memory that it is trying to access or not. Okay, so the base and the limit registers can be loaded only by the operating system, which uses a special privilege instruction. So we said that we should not allow unauthorized access to the operating system. Now, the base and limit registers that we have discussed just now, it can be loaded only by the operating system. And the operating system uses a special privilege instruction. And since privilege instructions can be executed only in kernel mode, and since only the operating system executes in kernel mode, only the operating system can load the base and the limit registers. So we have already discussed about kernel mode. So kernel mode is the mode in which operating systems execute. So user processes cannot execute in kernel mode. And we said that the base and limit can be loaded only by operating system which uses privilege instruction. And this privilege instruction can be executed only in kernel mode. And who can execute in kernel mode? Only the operating system can execute in kernel mode. So base and register can only be loaded by operating system and not by the user processes. So this scheme allows the operating system to change the value of the register but prevents the user program from changing the register's contents. So by following this scheme, this will make sure that only the operating system can change the value of the user registers, and the user programs cannot deliberately or accidentally change the register's contents. So with this, we have seen how we are able to protect the OS from unauthorized access, and also how we are able to protect the user programs from mistakenly accessing each other. Alright, so with this, I hope you are clear about the basic hardware structure, and also I hope you are clear with the issues that we have discussed, and also the remedies that we have discussed for solving these issues. So I hope this lecture was clear to you. Thank you for watching, and see you in the next one. In this lecture, we are going to discuss about address binding. So in the previous lectures, we have seen about the basic hardware structure of memory, and we have seen the importance of addressing in memory. We saw that the memory locations are given specific addresses, and it is using these addresses that we are able to access the memory location. So in address binding, we are going to see how different kind of addresses are given to programs or data present in different memory locations. So we may think that the address may always be absolute. That means we will always have a specific address for a process or the data present in a memory location. But that is not the case. So depending upon the stage in which a program is in the course of its execution, and by the course of execution I mean the stages of compiling, loading, executing and everything. So depending upon the stage that it is in, it can be given different kind of addresses. So that is what we are going to study in this address binding. So let's see what is this. So usually a program resides on a disk as a binary executable file. So this I have already explained. A program always resides on the disk, and by disk we mean the secondary memory. So the program, when it is not being used, it just resides or sits on the disk as a binary executable file. Now, to be executed, the program must be brought into memory and placed within a process. So this also is something that we have already discussed. When a program needs to be executed, it has to be taken from the disk and it has to be loaded into the memory. Then only the CPU will be able to access it and execute it. Now, depending on the memory management in use, the process may be moved between the disk and the memory during its execution. As we said, we need to have memory management. And why do we need memory management? Because we are going to share the memory between different processes, and we cannot always keep the process in the memory. And when I say memory, please note that I am talking about the main memory. So if we always keep a process in main memory, that is going to be inefficient. We need to keep it in main memory only when that process is currently in execution. So depending upon the memory management we use, we may have to move the process between the disk and the memory during its execution. So this movement between disk and memory will take place many times during the course of the execution of the program. So the process on the disk that are waiting to be brought to memory for execution form the input queue. So there may be processes that are waiting on the disk or on the secondary memory, which has to be brought to the main memory for execution. So they are waiting and forming a line there, and this forms the input queue. So here is a flow of how a process is executed. So we have the input queue, and what do we have in input queue? We have the processes on disk, okay, on the secondary memory that are waiting to be brought to main memory. So from the input queue, we select one process, and what happens? We load it into the memory. That means we load it into the main memory, and then what happens? That process, it executes and accesses the instructions and data from the memory. That means the execution is being done. And after the execution is done, what happens? That process will terminate. And after it is terminated, what happens? The memory space is declared available. So once a process terminates, that memory space is declared as available because that process no longer needs to occupy that place in memory. So that is declared as available so that the next process in queue can be taken and executed, or some other process can be executed. So this is the normal flow when a process has to be executed. Alright, so most systems allow a user process to reside in any part of the physical memory. So again, when I say physical memory, think that we are talking about the main memory. So most of the systems will allow a user process to reside in any part of the physical memory, and the part where it is residing up to its limit, that will be the legal address space for that particular process. And though the address space of a computer starts at 00000, the first address of the user process need not be the same. Though the address space of the computer starts at this, it doesn't mean that the user processes will always start at this one. Why? Because the system allow a user processes to reside in any part of the memory. Now in most cases, a user program will go through several steps during compile time, load time, execution time before being executed. So before a user program completely finishes its execution, it will go through several steps during these compile time, load time and execution time. So these are several stages that a process has to go through till it is executed. So there will be different steps that it will go through during these stages. And the addresses may be represented in different ways during these steps. So as I said in the beginning of this lecture, the addresses may not be absolute all the time. It may be represented in different ways during the different stages of execution of a program. So for example, during the source program stage, that means when the program is still in its source stage, the addresses are generally symbolic, such as count. So during this stage, the addresses may be a symbolic address. And then we have the compiler stage, that means the stage at which the compiler is compiling the program. So at that time what happens? Typically it binds the symbolic address to relocatable addresses, such as 14 bytes from the beginning of this module. So we said that when the program is still in the source stage, or when it is still a source program, the addresses are symbolic. Now when the compiling is going to be done, then these symbolic addresses are converted or binded to relocatable addresses. Like for example, 14 bytes from the beginning of this module. That means, let's say that there is a module from which the compiler is starting. Now we are saying that the address of this process will be 14 bytes starting from this module. So it is trying to give it some kind of relocatable address. It is not an absolute address, it is a relocatable address, because this could change. Later this can be changed to something else. So this is a relocatable address that is given by the compiler during the compile time. And then during the linkage editor or the loader phase, it binds a relocatable address to absolute address such as 74014. So at this stage, this is when the absolute address will be assigned to the process. So at compile time, it is having this relocatable address, and during this linkage editor or loader stage, these relocatable addresses are bound to absolute addresses such as this. So this is the time when absolute addresses are given. So we see that at different stages, the kind of addresses that are there are different, but they need to be binded to each other. So each binding is a mapping from one address space to another. So this is what is happening in the address binding. It is a mapping of one address space to another address space. So we need to keep track of where our program is, but also we need to make sure that we are mapping it to the right address space. Okay, so we will see a little bit more in detail about these stages, the compile time, the load time and the execution time, and how addresses are assigned during these times. So we will first discuss about binding of instructions and data to memory addresses during compile time. So in compile time, what happens? If we know at compile time where the process will reside in memory, then absolute code can be generated. So if we are sure about where the process is going to reside in memory at compile time itself, then we can give an absolute address for the process. We can say that this is the place exactly where the process is going to reside in memory. So for example, if we know our user process will reside starting at location R, then the generated compiler code will start at that location and extend up from there. So this is just like the base address that we talked about. So if we know where is it going to reside, that means if we know the starting location, so let's say it is R, so R is like the base, and we can say that from that base R, the memory location will extend up from there. So this is what happens when we know at compile time where the process will reside in memory. And then if at some later time the starting location changes, then it will be necessary to recompile this code. So at compile time we are saying that we know where the process will reside and we gave the absolute address for the process. But let's say that at some later time the starting address has changed. So at that time what will happen? We will have to recompile this code. So that is a disadvantage of this. So this is what happens if we know during compile time itself where the process will reside in memory. Alright, coming to the next one, we will be seeing what happens at load time. Binding of instruction and data to memory addresses during load time. So if it is not known at compile time where the process will reside in memory, then the compiler must generate relocatable code. So in the previous slide we saw that if at compile time itself, if we know where the process is going to reside in memory, then the compiler will generate the absolute code. But if the compiler does not know, or if during compile time we don't know where the process will reside in memory, then the compiler will generate a relocatable code. And what is relocatable code? I have just explained in one of the previous slides. And in this case what happens? The final binding is delayed until load time. If the starting address changes, we need to reload the user code to incorporate this changed value. So in this case, during compile time, the final address will not be generated. It will only generate a relocatable address. And then we wait until the load time for the final binding to happen. So at load time, we will be specifying the final address. And then if at some later point of time the starting address changes, we only need to reload the user code to incorporate this change value. We don't need to compile the whole program again. So in the previous one we saw that if we are declaring it during compile time itself and if the starting address changes at some later point of time, we have to recompile the whole program. But if we are binding the address only during load time and at some point of time if we have to change the starting address, then we only need to reload the user code to incorporate this changed value. So this is what happens if the binding is done during load time. Now coming to the last one, binding of instructions and data to memory addresses during execution time. So here we are trying to bind the addresses during the execution time, not compile time and not load time. So if the process can be moved during its execution from one memory segment to another, then binding must be delayed until runtime. So if we have an option where we can move the process from one memory segment to another during its execution, that means during execution itself, if it is possible to move the process from one memory segment to another, then we should delay the binding until runtime. We are going to give the final address during runtime only. So special hardware must be available for this scheme to work, and most general purpose operating system use this method. So this is a method that is used by most of the general purpose operating system. but we need to have a special hardware for this scheme to work, because we are moving the process from one memory segment to another during the execution time itself. So this is what can be done when we are binding the instructions and data to memory addresses during execution time. So as we have discussed, these are the three ways in which address binding can be done. It can be done during compile time, load time, and execution time. So these are all topics that are like prerequisites that we need to be clear about before we dive deep into memory management. So I hope this topic about address binding was clear to you. Thank you for watching, and see you in the next one. In this lecture, we will be discussing about logical versus physical address spaces. So we are going to discuss about two types of addresses, which is a logical address and the physical address. And we will also see what is logical address space and what is physical address space, how do they differ, and if they differ, how can they be related or how can we map one to another. Alright, so first of all, let us see what is a logical address. So logical address is an address generated by the CPU. So the address generated by the CPU is what we mean by logical address. And what is a physical address? An address seen by the memory unit, that is, the one loaded into the memory address register of the memory. So this is what we mean by physical address. It is an address that is seen by the memory unit. And what do we mean by seen by the memory unit? That means that is the particular address that is loaded into the memory address register of the memory. So just keep in mind that logical address is the address that is generated by the CPU, and the address that is seen by the memory unit or the address present in the memory address register of the memory is known as the physical address. Now, compile time and load time address binding methods generate identical logical and physical addresses. So in the previous lecture, we have studied about address binding and we saw different kinds of address binding. We have discussed about compile time address binding, load time address binding, and execution time address binding. Now the first two, that is the compile time and the load time address binding, if we are using these methods, they generate identical logical and physical addresses. That means in compile time and load time address binding methods, the logical address, that is the address generated by the CPU, and the physical address, that is the address seen by the memory unit, they are the same. It is identical. Okay? Now, in case of execution time address binding scheme, it results in differing logical and physical addresses. But in case of the execution time address binding, the logical address and the physical address that is generated, it differs from each other. They are not the same. So in this case, we usually refer to the logical address as a virtual address. So if we are talking about execution time address binding, since the logical and the physical addresses are different, we will refer to logical address as a virtual address. So when we say virtual address, just know that we are talking about logical addresses. So now we understood what is the meaning of logical address, what is the meaning of physical address, and we saw how logical addresses and physical addresses vary in different address binding methods. Alright, now let us see what is logical address space and what is physical address space. Now logical address space, it is a set of all logical addresses generated by the program. So from the name itself, it is very easy since you already understood what are logical addresses. So logical address space is the set of the logical addresses generated by a program. So for a particular program, the starting logical address to the ending logical address for that particular program, that will be the logical address space for that particular program. And similarly, physical address space is the set of all physical addresses corresponding to these logical addresses. So the physical address space will be the set of all physical addresses that corresponds to these logical address spaces. So when we say corresponding to these logical addresses, keep in mind that if we are talking about compile time or load time address binding, the address spaces will be the same because the logical addresses and the physical addresses generated during compile time address binding and load time address binding are the same. But in case of execution time address binding, the logical address space and the physical address space will be differing. So in execution time address binding scheme, the logical and the physical address spaces, they differ. They are not the same. So if they are not the same, how will we map them to each other? How will we know that for a particular logical address space, this is the corresponding physical address space? So how are we going to map them? So this is the problem that we have and the solution that we need to find. So how can we solve it? We can solve it using this. The runtime mapping from virtual to physical addresses is done by a hardware device called the Memory Management Unit or the MMU. So during runtime, we need to map the virtual address to the physical address. So as I already told you, when I say virtual address, remember that I'm talking about the logical address. So these virtual addresses has to be mapped to the physical addresses during runtime, and for that we are going to make use of a device called the Memory Management Unit, which is a hardware device. So let us see how does this Memory Management Unit work. example of dynamic relocation using a relocation register. Okay, so here we have the CPU, and here we have the MMU, which is a memory management unit, and here we have the memory. So the CPU generates a logical address. So let's say 238 is the logical address generated by the CPU. And this relocation register here, it will contain the starting physical address for the memory location for our particular program. So when we have discussed about the basic hardware, we have discussed about the base register and the limit register. So base register was something that stores the starting address of the address space of a particular process. So this relocation register is something similar to that. It will contain the starting physical address. Now, whenever a logic address is generated, we need to convert it to the corresponding physical address. So what we will do is, we are going to add the logical address to the address that is present in the relocation register. So here we have 15000. So the logical address is 238. So if we add them, we get 15238, which will be the corresponding physical address for this logical address. So the logical addresses, they will range from 0 up to the max value of whatever the logical address is. And the relocation register will contain the starting physical address value. And then we can get the corresponding physical address by adding the logical address to this address present in the relocation register. So for the CPU or for the user program, they think that the addresses are from 0 up to whatever is the maximum value in the logical address space. So let's say that, for example, for a particular process, the logical address space is from 0 to 300. So according to that user process, it only sees that 0 to 300. It does not have to worry about what is the corresponding physical address. Why? Because this memory management unit is going to take care of that. So the user process is only going to see from 0 to 300, and whatever it is trying to access will be added to this value here and will be converted to the corresponding physical address. So for example, if it is trying to access the first memory location, so what will be the value? It will be 0, because it starts from 0 to the maximum value, as we said in our example. So if it is 0, what will be the corresponding physical address? It will be 0 plus 15000. So it will be equal to 15000. So 15000 is the starting physical address for that particular process. So this is how we can make use of the memory management unit by this simple example of dynamic relocation using a relocation register to find the corresponding physical address for a logical address. So now we have two type of addresses: the logical address in the range of 0 to max, which I just explained now, and the physical address in the range of r plus 0 to r plus max for a base value r. So what is r? R was the value that was present in our relocation register. So in our example, it was 15000. So the physical address range is from that 15000 plus 0, and this 0 corresponds to this logical address. So r plus 0 to r plus max. So that is the physical address space that we have. So the user generates only the logical addresses and thinks that the process runs in locations 0 to max. So this is what is perceived by the user, because the user only sees the logical address space. The users think that it is only from 0 to max. But what happens inside? The memory management unit takes care of it, and it is converted to r plus 0 to r plus max, and that is the corresponding physical address. But the user does not have to worry about it. The user program supplies the logical address, and these logical addresses must be mapped to the physical address before they are used. And this is done by the memory management unit. So this is how logical addresses are converted to physical addresses. So we studied about logical addresses, physical addresses. We also studied about logical address space and physical address space, and we saw how these addresses are mapped to each other and how logical addresses are converted to physical addresses. So I hope this topic was clear to you. Thank you for watching, and see you in the next one. this lecture we'll be discussing about dynamic loading. So let us see what is this dynamic loading and what is it used for. As we have discussed so far, the entire program and all data of a process must be in physical memory for the process to execute. So this is something that we have discussed so far in this section of memory management and under this chapter of main memory. So we have said many times that when a program has to be executed, it has to be brought into the main memory. Only then the CPU will be able to access it and execute it. And at all other times when the process is not executing, it resides in the disk or the secondary memory. Now, the size of a process is thus limited to the size of the physical memory. So the size of a process will be limited to the size of the physical memory. So for example, if we have a physical memory of 1 GB, that means if we have a RAM or a main memory of 1 GB, we will be able to execute only a process of maximum 1 GB at a time. So if our process that we are going to execute is a very large one, let's say it is of 2 GB, anyway we are sure that we are not going to be able to accommodate that process in our main memory because it is too big. So we will not be able to load or run that process if we are trying to load it all at one time. So this is the limitation that we have. So in order to obtain a better memory space utilization, we can use dynamic loading. So in order to solve this problem, we are going to use something called dynamic loading. And we are going to use dynamic loading in order to obtain a better utilization of our memory space. Now, let us see how we can do it and how dynamic loading is going to help us to achieve this. So with dynamic loading, a routine is not loaded until it is called. So with dynamic loading, we are not going to load the complete program into the memory once it is to be executed. But we will be loading only parts of that program which we will call routine, and they will be loaded into the memory only when it is needed. So we may have a big program. We may have a big program with multiple sections. So let's say that we have multiple sections or let's say multiple functions. So during the course of execution, the entire functions may not be required all the time. So there may be a particular time when one portion of code or one routine is required, and there may be another time when another portion is required. So we will be loading only that portion when it has to be used or when it has to be called. So in that way, we don't have to load the entire program into the memory, but we will load only the particular parts that we need. Hence, we will be making better utilization of our memory space. So what we'll do here, all routines are kept on disk in a relocatable load format. So all the routines will be kept in a disk. So disk means secondary memory. So they will be kept in a disk when they are not in use in a relocatable load format. And then the main program is loaded into memory and is executed. So the main program, that means the main function, will be loaded into the memory. And when we say memory, it is the main memory. So we'll be loading the main program into the memory and it is executed. And then what happens? When a routine needs to call another routine, the calling routine first checks to see whether the other routine has been loaded. So during the course of execution, let's say that we have loaded the main program into the memory and the routine from the main program needs to call another routine. Now what will happen? It will first check if the routine that it is trying to call is already present in main memory or not. And if it is already present, well and fine, it can be executed. But if it is not present, what happens? The relocatable linking loader is called to load the desired routine into memory and to update the program's address tables to reflect this change. So if the particular routine that is being called is not present in memory, then what happens? By this point, what we mean is we are trying to call that routine. So that routine will be called, and using this linking loader, it will be loaded from the disk, that means from the secondary memory into the main memory. So when we need it, we are just calling it and we are loading it into the main memory and we are using it. And at all other times, it remains in the secondary memory. And after that, the control is passed to the newly loaded routine. So that means after loading that routine, the control is given to that particular routine and it can do its execution whatever it is supposed to do. So this is how dynamic loading works. So we see that we are loading something only when we need it, and at other times it will be kept in the disk. So hence we don't need to load the entire program into the memory. So coming back to the example that we took, suppose we have only 1 GB of main memory and the program is of 2 GB. So what we'll do, we are not going to load the entire 2 GB. Anyway, it is not possible. So we will load the main program provided that that is less than 1 GB, and then only those parts or routines that are currently needed will be loaded into the memory, and hence we can try to make that program work even though the main memory is less than the size of the program. So this is how dynamic loading works. Okay, so let us take a look at the advantages of this dynamic loading. So from the explanation itself, you must have already understood what are the advantages, but anyway, let's take a look. So an unused routine is never loaded. So as I just explained now, whatever is not used, it just resides in the disk and we are not loading it, and we are not filling up our main memory unnecessarily. And then this method is particularly useful when large amount of code are needed to handle infrequently occurring cases. So this is also something I have already explained. If our code is very large and we need to handle infrequently occurring cases, then this method is useful because we don't need to load the entire big amount of code, and we just need to use a particular portion of that code which is needed at that point of time. So although the total program size may be large, the portion that is used and hence loaded may be much smaller. So this is also something that I have just explained. Now, dynamic loading does not require special support from the operating system. It is a responsibility of the user to design their programs to take advantage of such a method. So this dynamic loading does not require special support from operating system, and it is a responsibility of the user, that means the person who is designing their program, to take advantage of this method and make sure that their program is able to function in this way. That means it should be able to load only what is needed at the particular point of time, and the other portion can reside in the disk. So it is a responsibility of the programmer or the user to take advantage of this method. Alright, so those were the advantages of dynamic loading, and I hope you understood how dynamic loading works, why it is useful, and how it helps in making our computation faster and more efficient. So I hope this topic was clear to you. Thank you for watching, and see you in the next one.